In order to advance our understanding of sampling distributions, a key concept that we must first learn is sampling error. And that brings us to the question, what is sampling error? Simply put, if I had to explain this to a friend, I would say that it is information gathered from a sample compared with information gathered from the entire population and trying to map out the difference. So, in statistics, the word error is not necessarily used in the sense of a mistake. Rather, it is used in the sense of the difference. So, in this context, when we talk about sampling error, it is simply looking at information we extracted from a sample and comparing it in terms of its difference to information you would otherwise have obtained if you took data from the entire population. Let's take a more realistic example to bring this down to reality. Let's say you work in a company where they manufacture fireworks. The entire population in this case will be the entire population of all fireworks that have ever been produced. In order to understand or check if the fireworks are functioning great or will work great for the purpose for which it is intended, no one will decide as a quality engineer to set off all the fireworks all in the name of saying, hey, we just want to check if they work. No, nobody does that. What the quality engineer would likely do is take a randomly drawn set of fireworks, set it off. If it works well, then there is some assurance, some degree of assurance or certainty that this information that you gathered from the sample of fireworks you chose and set off will tell you about how others in the same batch or for the entire population will work. So, if what you got from the sample says all the fireworks are working well, that will be information from the sample. But that does not guarantee that all fireworks in the entire population will also work well, just as it was true for those in the sample. That difference is what we call sampling error in statistics. So this would be a way to explain it in layman terms. Now let's get to the examples of the theoretical in-class understanding of sampling error. In order to compute the sampling error, we would use the formula that says that the sampling error would be the sample mean, x bar, minus the population mean. So in this example, we're told that a population has a mean of 125, which means that the population mean mu is 125. Now, a random sample, if a random sample of 8 items from the population results in the following sampled values, these are the sampled values. The question is, what is the sampling error for the sample? All we need to do is remember this formula being highlighted on your screen. The sampling error will be equal to the sample mean in English. In statistics, I don't like writing too many words. I'll just write x bar and then minus the population mean, which is written as the letter U, then with an extension on the left, and take the difference. So in this case, it means I need 2 ingredients. 1, the sample mean, 2, the population mean. Which ones did the question give me already? I was given the population mean. The population mean is 125. So 125 here is set. I'm only left to find the sample mean as the second ingredient to cook this soup called the sampling error. So I need to get the sample mean from the sampled values, which means I will go here, I will add up all of the values, 103 plus 123 up until 99, and then divided by how many values do we have? 1, 2, 3, 4, 5, 6, 7, 8. So I'll go ahead, write the 8, and that will be x bar, the sample mean is 106.5. We can do that if you check out the chapter or module 7 data sets. I have the data values right here. You can add up all the data values. Oops, excuse me. So I'm going to click here and then drag over, and you can see the total here, and you can see the average here, which is 106.5. So I can take that back here, and that means I have the second ingredient I need. So I can write that here, 106.5 minus 125, this will equal to negative 18.5. This is the standard error. So just to confirm and emphasize, the standard error is always the sample mean or information that summarizes the sample minus the population mean. That is, the information we would otherwise get if we are able to expend all efforts to gather information from the entire population. Let us move on to the next example on the next page. This question says that assume that the following represent a population of values. So this time, we're given the entire population of values. In the last example, we only had the sample values. So we proceed then to question A. If a random sample of n equals 10 items includes the following values, which means the sample, in the first sample drawn, we got these data values. We're to compute the sampling error for the sample mean. Okay, this sampling error is equal to the sample mean x bar minus the population mean, which means I would need to get the sample mean from the sample values, which would necessitate adding up all of these data values and dividing by how many were added together. And I can go, if I have the data values already in Excel, I can do that in Excel. So let's see. So here in Excel, in column C, I have the data values. I can highlight them, and I have the average here. The average here is 18, so which means that for this sample, the average is 18. And for the population, I would need to get the population mean. So again, in a similar vein, I will need to add up all the data values and divide by the number of data values here. I have already keyed in all the data values here in this column. So I'm going to highlight the entire data values, and I have the average here, which is 22.125. So with that, I can go back to my working space, and I have 22.125. So now that I have the two ingredients I need, x bar, which is 18, I can write that here. I have 18 minus 22.125, and that will give me negative 4.125 as the value of the standard of the sampling error. Then we proceed to question B. For a sample of size n equals 6, compute the range for the possible sampling error. Take note, in this case, we're looking at the range for the possible sampling error. What this requires is that we follow the int, and in following the int, we'll first find the sampling error for the 6 smallest sample values and the sampling error for the 6 largest sample values. What does that entail? I'm going to split this into two. Step one, I am first going to sort the entire population data values from least to highest. For the sake of emphasis, the first step will be to sort all the population values from the least to the largest. That means I'm going to need to arrange this from the smallest to the largest value. In order to sort the data values, I will go into Excel. I have all the population values here. So all I need to do is first highlight the data values, and I'll need to sort from smallest to largest. So go ahead. So if you see on my screen, it is saying that Microsoft Excel found data next to your selection, and Excel has also observed that I did not select this data, and is asking me that since I did not select that data, that this data would not be sorted. So what do I want to do? Do I want to sort the data values to the right of the column I highlighted? Well, I do not. So I would like to continue with just that column, the current selection. So click on Sort. So as you might observe, in column B, I now have all the values automatically sorted from the least to the largest. Well, back to the question. I will need to find the sampling error for the 6 smallest sample data values. So my step 2 in this case will be to find the average of the 6 smallest sample values. So back here, I will try to grab the 6 smallest data values, which is 6, 6, 9, 10, 10, and 11. And as you can see, the average there is 8.6667. So in this case, my step 2 would be to get the sampling error for the smallest 6 values, and that will be the average of the 6 smallest values, which is 8.6667 minus the original population mean, which is 22.125, and that will give negative 13.458. So again, just to remind us, after sorting the data values from the least to the largest, we got the average of the 6 smallest values minus the general population average or mean, and we have the standard error for the smallest 6 data values. So step 3 then would be to proceed to find the standard error due to the 6 largest sample data values. So standard error for the 6 largest data values, I will need to get first the average of the largest 6 values. So I'll go from the bottom, 1, 2, 3, 4, 5, 6. These are the 6 largest data values, and their average is about 33.167. So I'll take that to my working space, 33.167 minus the general population mean, which is 22.125, and that will give me 11.042. With these 2 values I'm highlighting, I am ready to indicate the range. So I can say in step 4 that the range for the possible sampling error would go from negative 13.458 to 11.042. Let's write that down. So as iterated earlier, the range for the possible sampling error is from negative 13.458 to 11.042. We're going to do a similar problem in question C. This time, we'll try to increase the sample size from size 6 for a typical sample to size 12, just to see what effect it has on the sizes of the sampling error. So again, we'll follow a similar step. Step 1, we'll sort all the population values from the least to the largest, which we have done earlier. If we go back to our Excel file, this is already sorted in column B. Then the next step would be to determine the standard error for the smallest 12 data values. So I'm going to go ahead. I'm going to note that my step 2 will be the standard error due to the smallest 12 values. This will be equal to, I need to grab the 12 smallest data values, 1, 2, 3, this is 6, and this is 9, and then this is 12. And what do I have for the average? 12.917. So I'll take that back to my working space. This is 12.917 minus 22.125, the general population mean, and this will be equal to negative 9.208. Then step 3 will be the standard error due to the largest 12 values, and this will be equal to, I need to get the 12 largest values. This will be this way, and to illustrate this, I'm going to do this again. So 1, this is 3, this is 6, this is 9, and this is 12. So in this case, we see that the average of the 12 largest values is 31.333. So I'm going to take that over here. I have 31.333 minus 22.125, and this is equal to 9.208. So in step 4, I have an answer. And the answer is to state that the range for the possible sampling error for size 12 is from negative 9.208 to 9.208. So it stands to reason that based on our calculations, for samples of size n equals 12, the range of possible sampling error is from negative 9.208 to positive 9.208. Now, it's time to step back and reflect. When we picked a sample of size n equals 6 in question B, we had this sizes of the sampling error. But then when we increased the sample size to size 12, what happened to the standard errors? They appeared to become smaller. Well, what do we observe? We can say that as the sample size gets bigger, we seem to be having a lesser amount of sampling error. Why do you think that is so? I'd like you to reflect on this in the background as we proceed to the next example on page 6. This question says that a computer lab at a small college has 25 computers. Twice during the day, a full scan for viruses is performed on each computer. Because of the differences in the configuration of computers, the times required to complete the scan are different for each machine. Records for the scans are kept and indicate that the time in seconds required to perform the scan for each machine is shown here. So, question A. What is the mean time required to scan all 25 computers? So, for all 25 computers, that would be for the entire population of all computers that we have. Since it pertains to all computers that we have, that means we're talking about the entire population values in this case. So, the only mean we can be calculating here is the population mean, which is denoted by mu, and that would mean we need to add up all of these data values and divide by 25. So this is a good time to call on our good old friend Excel to help us with the computation part. So going back into Excel, I am going to highlight all the data values, and I have my average. So this is average of 1432 seconds. So I have the population average 1432 seconds on average for all 25 computers. All right, then for question B, suppose a random sample of 5 computers is taken and the scan times for each of those 5, for all 5 computers, is 1534 up to these values. If these 5 randomly sampled computers are used to estimate the general population mean for all 25 computers, what would be the sampling error? Remember, sampling error is the average from the sample minus the population average. So in this case, I will need to get X bar, that is the average of all these data values, 1534 up until 1834. To help me with that, I would go to Excel and I'm going to highlight these data values right here, and I have the average here, which is 1519. So I'll take that back. So I have 1519. Let's see, 1519 minus 1432. Remember, that is the population mean, and that will be equal to 87 seconds as the size of the sampling error, which means that if I had decided not to take data from the entire 25 computers and I decided to just go with this random sample of 5 computers, my estimate of how on average, my estimate of how on average it takes a computer to scan the to complete a scan rather, would be off by 87 seconds. Again, this is the true average. If I had estimated by using this sample data that gives me the sample mean of 1519, I will be off from the true population mean by 87 seconds. This will be the English description of what calculation we have done here. With that said, we proceed to question C. Here we would like to answer the question, what is the range of possible sampling error if a random sample size of 7 computers is taken to estimate the mean scan times for all 25 machines? Well, in this case, we note we're interested in a range and given the sample size of 7. So what would I do? I would do something similar to what we did in question B and C here, which is start off with sorting all the data values in Excel. So going into Excel, I'm going to highlight all the data values, and I'm going to go to sort and filter, click on the arrow down, and sort from smallest to largest. I would like to continue with the current selection and sort. So now it is sorted, and I would like to choose a sample of what size? Size 7. So to choose a sample of size 7, I'll pick the 7 smallest values, 1, 2, 3, 4, 5, 6, 7, and I have the average of the 7 smallest values. So to begin with, I can take the standard error for the smallest 7 values. This will be equal to 1256, right? Minus the general mean, which is 1432, and this will be equal to 176. And then I would compare with the standard error. If I had chosen the largest 7 values, then that will be equal to, going back into Excel, I'm going to choose the 7 largest values. This is 3, this is 6, this is 7, and it has a total of 1611. So, an average of 1611. So we take that back here, 1611 minus 1432, and that will be equal to 179. So based on these results, I can say that the range of possible sampling error for a fixed random sample of size 7 is from negative 176 to 179. Again, sorry about that. This should be negative 176 to 179. So, based on the two examples we've done, we can tell that in general, there's a truth here, that the larger the sample size we select, the smaller or lesser the size of the error we make when estimating the unknown population mean. Now, why does this make sense? Remember I said we would come back to this? Well, if you have chosen to cook a pot of chicken noodle soup, if you choose to eat all the whole pot just to taste if you have enough seasoning, that would probably be an overkill. The reality is, the information you get from a small spatula might not be the same amount of information you get if you had put some amount of that soup in some bowl that you can place on the table. As the size of what you scoop increases, there is an increased likelihood that the information you get from that small portion you took would not compare with what you get from a larger portion from the same population. In general, the larger the sample, the more reliable or the closer the information you get will come to the information you will otherwise get if you sample the entire population.